I'd like to do an example using dimensions right now. This is important. You should always write your units because you're going to need to keep the units straight. Again, I explained this earlier, but you always need to keep track of the units. We sometimes have to change units. So imagine we have a cube, and the cube is 12.0 centimeters, 12.0 centimeters, 12.0 centimeters. Okay, and I want to know the volume. Well, that's going to be 12.0 centimeters cubed. Okay, and so that's going to be equal to 1730 cubic centimeters, using our rules for significant figures. Okay, all right, now, problem. I want the answer to be in cubic meters because I'm going to fill my cube and I'm ordering some bulk powder or something to fill my cubicle box and it comes in cubic meters. I need to know how many cubic meters to order. And so I asked, how many cubic meters is 1730 cubic centimeters? Well, a lot of people will tell me you move the decimal over 2 places. So 17.3 cubic meters. Is that right? The answer is no. Because 12 centimeters is equal to 0.12 meters. So the volume is going to be 0.12 meters cubed. Well, if you multiply that out, that's 1.73 times 10 to the minus 3 cubic meters. Oh, wait, what happened? This is a huge difference between here. This is a factor of a million difference here. 10 to the 6 difference. So it's not 10 to the 6, but this is a huge difference here, between 17 and 1.7 times 10 to the minus 3. So I guess that's a factor 10 to the 4. So that's 10,000 difference, So if you ordered 17.3 cubic meters to fill your box, it only holds 1.73 times 10 to the minus 3 cubic meters. You're going to get 10,000 times too much stuff. And so what happened? Well, we have 3 of these centimeters. So you have to move the decimal over 1, again, and again. Okay. And so that's why you got the 1.73 times 10 to the minus 3 cubic meters. So that's a very important thing right there. The other thing, you multiply units. So again, let's say we have a box here and I want to find the volume of it. And this length right here is 4.75 centimeters. The height is going to be 1.81 centimeters. And let's say the width is going to be, let's say that the width is going to be 2.88 millimeters. So if I want to find the volume, you have to multiply. Okay, so 4.75 times 1.81 times 2.88. And if you're not careful, you'll write down this. And so the problem is, what's the problem? Well, the problem is it's not going to be right. Because what you get is 24.8. Okay, but the problem is this was centimeters, that was centimeters, that was millimeters. The units did not work out. Okay. You can write down centimeter cubed here, and that's wrong. That's not the right answer. Okay, because this up here, it needs to be converted. So that needs to be converted to 0.288 centimeters. And so that changes the answer here to 2.48 centimeters cubed. So what you have to do is up front, make sure all the units are right. Now, for a student solving a problem, this is very important. If you're solving the problem, write the units as you're solving the problem. I know it takes extra effort. Do it anyway. Most of you, again, want to be science or engineering. A good scientist is not the first one to solve a problem. A good scientist is the first one to solve it right. Right now, we're working on a vaccine for this coronavirus. The first vaccine to come out is not any good if it's not done right. You need the right sort of vaccine that comes out. So if you make a mistake, but you're still first, it doesn't work. The engineer that is the first to, so in other words, you have a company that wants to build a bridge that goes over a highway bridge or something, so they hire an engineering company to help them design these parameters of the bridge. The team of engineers that gets the bridge first is not necessarily the best. You want the team of engineers that's the first to get it right. Okay, you don't want to build something and have it fall down because you forgot a unit somewhere. Again, this sort of problem happens now again. Within just the last few years, they were building a pedestrian bridge in Florida, and there was a team of engineers that designed the thing, but they slipped up a little bit and on units, and bridge fell down, as they were building it, and people died. So what you need to do is make sure you keep track of the units at every step of the problem. And if you do, then that's going to save you problems later on. Well, dimensions, units, this can actually help you otherwise. So for example, I have a spring, okay, and I am told that my spring here has something called a spring constant, and the spring constant is going to be equal to 12.4 newtons per meter. So this is the units of a spring constant. And I want to stretch my spring here a distance of 4.75 centimeters, and I want to know how much force does it take to do that. Okay, so the distance I want to stretch is 4.75 centimeters. Now, much later in the semester, we are going to cover something called Hooke's Law, which tells us how to solve this problem. But it turns out you don't need Hooke's Law to solve the problem if you know basic sort of things. Unit of force is a Newton. So I want to get a Newton out of here. So how do I get a Newton? Well, up here, I have Newton per meter. I want to get rid of a meter. Well, how do I get rid of the meter? I multiply by meters. Well, gosh, that's centimeters. Well, wait a minute. That's the same as 0.0475 meters. So if I take 12.4 Newton per meter and I multiply by 0.0475 meters, the meters cancel. And so the answer, 12.4 times 0.0475, turns out to be 0.589 newtons, and that is actually the correct answer. That's how hard it takes to stretch the spring that distance. if that is the spring constant. You didn't have to know Hooke's law to figure this out. You just had to know that if you multiply Newton per meter by meter, the meters cancel and you get newtons, which is what you wanted. And so this is a tool of dimensional analysis. And that's very, very powerful. So on a test, you might not have known how to solve the problem, but you did know if you multiply this times that, it comes out the right units. Well, bizarrely enough, that works about half the time. Whereas just randomly throwing things together almost never works. And so this is a very powerful strategy. Okay. So I'm going to do another example here with units next. And that'll show you yet one more powerful thing that units can do.